100 years of physics tells us that collective atomic vibrations, called phonons, can behave like particles or waves. When they hit an interface between two materials, they can bounce off like a tennis ball. If the materials are thin and repeating, as in a superlattice, the phonons can jump between successive materials. Now there is definitive, experimental proof that at the nanoscale, the notion of multiple thin materials with distinct vibrations no longer holds. If the materials are thin, their atoms arrange identically, so that their vibrations are similar and present everywhere. Such structural and vibrational coherency opens new avenues in materials design, which will lead to more energy-efficient, low-power devices, novel material solutions to recycle and convert waste heat to electricity, and new ways to manipulate light with heat for advanced computing to power 6G wireless. Their paper, Emergent Interface Vibrational Structure of Oxide Superlattices, was published January 26 in Nature. Eric Hoagland, a postdoctoral researcher at the University of Virginia School of Engineering and Applied Science, took point for the team. He earned his Ph.D. in Materials Science and Engineering from UVA in May 2020 working with James M. Howe, Thomas Goodwin Diggs Professor of Materials Science and Engineering. After graduation, Hoagland continued working as a postdoctoral researcher with support from Howe and Patrick Hopkins, Whitney Stone Professor and Professor of Mechanical and Aerospace Engineering. The ability to visualize atomic vibrations and link them to functional properties and new device concepts, enabled by collaboration and co-advising in materials science and mechanical engineering, advances MMI's mission, Hopkins said. We came up with an explanation that fit the conductivity measurements, but always felt this work was incomplete. It turns out, when the interfaces become very close, the atomic arrangements unique to the material layer cease to exist, Hoagland said. This explains why nanoscale spaced interfaces produce unique properties, different from a linear mixture of the adjoining materials. Hoagland collaborated with Jordan Hachtel, an R.D. associate in the Center for Nanophase Materials Sciences at Oak Ridge National Laboratory, to connect local atomic S. Working with high spatial resolution spectroscopic data, they mapped interlayer vibrations across interfaces in a superlattice. That's the major advance of the Nature paper, Hopkins said. We can see the position of atoms and their vibrations, this beautiful image of a phonon wave based on a certain pattern or type of atomic structure. The collaborative trek to collective success. The highly collaborative effort began in 2018 when Hoagland was sharing research plans to characterize The experiments that Jordan and I did at Oak Ridge boosted our confidence in using superlattices to measure vibrations at the atomic or nanoscale. During one of his later trips to Tennessee, Hoagland met up with Joseph R. Matson, a Ph.D. student conducting related experiments at Vanderbilt Univ. Using Vanderbilt's instruments, they conducted Fourier transform infrared spectroscopy experiments to probe optical vibrations in the entire superlattice. From these experiments, Hoagland deduced that the properties he cared about, thermal transport and infrared response, stemmed from the interface's influence on the superlattice's well-ordered framework of oxygen atoms. The oxygen and metal arrangements in this framework generate the unique vibrations and give rise to the material's thermal and spectral properties. Up to this point, Ramamurthy Ramesh, University of California, Berkeley, professor of physics and materials science and engineering, and his Ph.D. students Ajay K. Yadav and Jayakanth Ravichandran were the growers on the team, providing samples to Hopkins' X-Site research group. We realized we had all of this really neat experimental data connecting vibrations at atomic and macroscopic length scales, but all of our explanations were still somewhat conjectures that we could not prove absolutely without theory, Hoagland said. Their theoretical and computational methods supported exactly the results produced by Hoagland and other experimentalists on the team. The simulation also enabled the experimentalists to understand how every atom in the superlattice vibrates with high precision and how this was related to structure. At this point, the team had 17 authors, 3 microscopists, 4 optical spectroscopists, 3 computational scientists, 5 growers and 2 material scientists. It was time, they thought, to share their findings with the scientific community at large. An initial peer reviewer of their manuscript advised the team to establish a more direct, causal connection between material structure and material properties. We measured some cool new phenomena making connections over multiple length scales that should affect material properties, but we had not yet convincingly demonstrated whether and how the known properties changed, Hoagland said. 2 graduate students in Hopkins X-Site Lab, senior scientist John Tomko and Ph.D. student Sarah McCarrim, helped provide the final proof. When you send in a photon of 1 unit of energy, the superlattices double that unit of energy, Hopkins said. John and Sarah built a new capability in our lab to measure this effect, which we express as the second harmonic generation efficiency of these superlattices. Their contribution expands the X-Site lab capabilities to understand new light-phonon interactions. I fully expect we will find that these phonon waves, this coherent effect, exists in a lot of other materials. The long-standing collaboration continues. Retrieved February 4, 2022 from ift.tt/lgxjvzd University of Virginia School of Engineering and Applied Science. https://ift.tt/lgxjvzd. Accessed February 4, 2022. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.